So we already learned about what happens when metals and nonmetals transfer electrons. What happens is they form an ionic bond. But when nonmetals and nonmetals share electrons, what happens is they form a covalent bond. So atoms tend to bond to lower their potential energy. So this diagram that we're looking at here starts actually over here, believe it or not. So over here, we have two hydrogen atoms that are really, really far apart at the atomic level. And as they get closer and closer together, as they move closer and closer together, there is some small amount of overlap and there's some attraction. At this point, we call that the sweet spot, and that's where the atoms actually share electrons, and as a result of them sharing electrons, they stick together. But if you squish them together too much, then they actually repel each other. So what's happening here is that the positive nuclei of one atom is attracted to the negative electron of another atom. But here's the thing. If they are close enough, that positive nucleus and negative electron are really, really good, and then they're stuck together. But if they're too close, so this is bonding. If they're too close, the positive nuclei of one atom will repel the positive nucleus of the other atom. That's if they're too close. So when bonding occurs, they have to be at just the right distance apart. We can measure that, but it's not really important in terms of how we do that. Now, atoms want to gain, lose, or share electrons so they have a more stable arrangement of electrons in their valence shell, and they all want to have what we call the octet rule, which means they have 8 electrons. The exception to this rule would be atoms like hydrogen, or atoms like would be atoms like hydrogen, or atoms like helium, or atoms like lithium. Well, yeah, lithium, or atoms like beryllium, or atoms like even boron. Okay, so hydrogen, helium, lithium, beryllium, boron. So hydrogen has an electron configuration of 1s1. Helium has an electron configuration of 1s2. At this point, helium is satisfied. It has a full outer shell. Even though it's not 8 valence electrons, it has 2 valence electrons because that s sublevel is full. Lithium has an electron configuration of 1s2, 2s1, and beryllium has 1s, that's not right, 1s2, 2s2, and boron has 1s2, 2s2, 2p1. So in this case, what ends up happening is that if lithium loses an electron, gone, it now has a stable energy level of 1. And if beryllium loses 2 electrons, right, it now has a stable energy level, and that first energy level only needs 2 valence electrons. And boron kind of does the same thing. So these are the exceptions. The other thing that I want to tell you is that usually the number of valence electrons can dictate how many bonds an atom can form. This is not always true, but it is true most of the time. So if an atom has one valence electron, it can usually form one bond. If an atom has two valence electrons, it can usually form two bonds. So let's talk a little bit about how we do this, and then we'll go through a couple of examples, and then you'll have homework time. So you always count the number of total valence electrons. This is your bank, and you have to use all the electrons in the bank. You can't use any more, and you can't use any less. You figure out your center atom. It's usually the single element in the chemical formula. It's never hydrogen, and if carbon is present, it's almost always carbon. Connect the elements to center atom, subtract from your bank, and then check to see if all elements are satisfied using the octet rule. And if you need a triple bond and you have oxygen, put the double bond there. And we'll just go through a couple of examples. Also, when we draw bonds, we draw a line. One line equals 2 electrons, and that's going to be super important as we go through some examples. So example number 1, modeling covalent bonding, hydrogen. So I see that I have hydrogen, and I have which has 1 valence electron, but there's 2 of them in this formula, so I have 2 total valence electrons to find a home for. So I'm going to have hydrogen, and I'm going to bond it to the other hydrogen by drawing a line, and I said just a second ago that one line equals 2 electrons, so I've used all of my electrons, so this would be the structure for H2. Getting a little bit more complicated, I have nitrogen, which according to the periodic table has 5 valence electrons, and there's 1 of them. And then I have hydrogen, which has 1 valence electron, and there's 3 of them, so 3 valence electrons. And so I add that up, and I have a total of 8 valence electrons to find a home for. So the central atom is usually the singular one, so I'm going to start with nitrogen and put it in the middle. I'm then going to bond hydrogens to it, and I'm going to try to spread the hydrogens out kind of as far as I can, just because they don't want to be near each other. And then I'm going to draw a line connecting each hydrogen to the nitrogen, and I see that each line is equal to 2 electrons. So there's 3 lines. Well, let's see, 1 line, no, 1 dash equals 2 electrons. 3 dashes equals 3 times 2 is 6 electrons. So I've used 6 electrons, so in this case I have 2 more electrons to find a home for. Well, the only thing that can have it is the central atom in this case, which is nitrogen. So now nitrogen has 2, 4. It has 2, 4, 6, 8. So there's 2 electrons here, 2 electrons here, 2 electrons here, 2 electrons here, so nitrogen has 8 valence electrons and it's satisfied. Hydrogen is one of the exceptions, and hydrogen has 2 valence electrons, each of them, so it's satisfied. So that's great. We're going to do a little bit more complicated one. Here we have carbon, which has 4 valence electrons times 1 of them, so that's 4 valence electrons. We have chlorine, which has 7 valence electrons times 4, which is 28 valence electrons, and then we're going to add that up to get a grand total of 32 valence electrons to find a home for. So I'm going to start with my central atom, which is carbon, and I'm going to take my 4 chlorines and I'm going to bond them to carbon as far apart as I can from each other, and then I'm going to draw a single line. That single line indicates 2 electrons, and I've got 4 single lines here, so it's 2, 4, 6, 8 electrons around carbon. So I've used 8 electrons, and 32 minus 8 is, let's see, 12, 4, so that's 24, nope. Yeah, 32 minus 8 is 24 electrons to find a home for. So I'm going to go ahead and start placing electrons around chlorines in pairs, 2, 4, 6, 8, 10, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. So in this example, all of the chlorines have 8 valence electrons, the carbon has 8 valence electrons, and everybody's satisfied. Clearly we have to make things a little bit more complicated because that's what chemists do. Here I have oxygen with 6 valence electrons times 2, which is 12 valence electrons total. That's all I got. So I'm going to take oxygen and I'm going to bond oxygen to itself. with a single line. So I'm going to subtract 2 electrons there, and that gives me 10 electrons to find a home for. So I'm going to start placing 2, 4, 6, 8, 10. Now I've used all my electrons, and the problem that I see with using all my electrons is the oxygen on the right is satisfied. The oxygen on the left does not have 8 valence electrons. So what I'm going to have to do is I'm going to have to remove some electrons from one and put it somewhere else. And what I'm going to do is I'm going to get rid of that pair of electrons and create a double bond. So I'm going to redraw this. Oxygen, oxygen, single bond, double bond, and then I have these 2 electrons here and these 4 electrons here, and now oxygen on the left has 2, 4, 6, 8 with the 2 lines, and oxygen on the right is 2, 4, 6, 8, and so everybody's satisfied. One final example, carbon has 4 valence electrons times 2, which is 8 valence electrons. Hydrogen has 1 valence electron times 4, so that's a grand total of 4 valence electrons. I add all that up and I get a grand total of 12 valence electrons. This one's tricky because I have 2 carbons and 4 hydrogens, so one of them, so there's no actual center. So when that happens, a lot of times this happens with carbon, they usually kind of end up in the middle anyway. So I'm going to bond the 2 carbons together, and then I'm going to bond the 4 hydrogens together. And if I bond the 4 hydrogens to the carbon like this, it becomes really clear that one carbon will be okay and the other carbon won't. So what I'm going to do is I'm going to spread my hydrogens around, just because that makes a little bit more sense in terms of the arrangement of electrons. So I'm going to spread them out like this. I'm going to add bond here, bond here, bond here, bond here. So at this point I've used 2, 4, 6, 8, 10 electrons. And the hydrogens are satisfied, but the carbons are not. So I'm going to add that double bond right there, and now everybody is satisfied. So now that we have completed this, what you can do is you can go ahead and complete the covalent naming or the covalent structure worksheet in your packet, and good luck.